Hello everyone, I'm Sirisha Viala, and today I'm going to talk about my project Human Activity Recognition, basically the accelerometer data analysis. In our current world, where people are increasingly focused on health and fitness, the demand for personal activity monitors has also increased. The unpredictable nature of fitness, particularly during the COVID-19 pandemic, it underscores the need for innovative solutions like some fitness monitors or like Body Media and Fitbit. And our main goal was to design and implement a machine learning model capable of accurately identifying and classifying various human activities based on sensor data. We aimed for a device capable of distinguishing activities like walking, running, sitting, standing, and more. Our project framed the challenge as developing a robust machine learning model for human activity recognition based on sensor data. The dataset was utilized contained recordings of various physical activities, each associated with sensor readings from accelerometers worn at different body locations. As you can see here, we have 8 hours. We have collected 8 hours of accelerometer data for four individuals, which will later be discussed through their showing their individual height, weight, and parameter through a table. And here we can see that each subject has worn a sensor at different locations in the body, and five activities have been recorded throughout the sessions with a 150 milliseconds of time window. And data pre-processing was very crucial. We retained duplicate rows to capture repeated actions and addressed outliers using IQR rule. And we have also conducted some imputation methods to handle the outliers effectively. We utilized some of the feature engineering and scaling methods, and some of them are like one-hot encoding and also label encoding of each activity classes that we have noted down. And later we have used to do some feature scaling, which will enable us to make sure that the model can take the sensitive is not sensitive to the data that we are using for the analysis. And coming to demographic factors of uses, as we discussed earlier, Deborah, Jose, Carlos, Katia, and Wallace are the four subjects that we have used to um, conduct our research. And here are the here are the age, height, weight, and BMI of each subject. And we can see that the number of instances of each activity in class has been has is imbalanced, and we can clearly observe here that sitting down, standing up values are least, whereas sitting, standing, and walking class are comparatively up here and there, more or less similar to each other. And here, the below table shows the outliers of each class with respect to each coordinate value. Here we can see x1, y1, z1 are the sensor one coordinates. Likewise, we have x2, y2, z2 for sensor 2, and so on. And we can also see to understand more, to visually understand more about these outliers, we have given some box plots and also some other kind of graphs. Here you can see how these outliers are away from each, like each coordinate and separated by each sensor. Likewise, we have also given scatter plots, which I found to be really efficient to understand the outliers clearly. And then I have also plotted, after doing some encoding and label encoding of each activity class, I have plotted them in a 3D scatter plot to examine the data points of each activity closely. And here, if we see that, we can observe this is the temporal graph of each activity. And we can observe that for sitting and standing, it almost seemed to be constant throughout the session, um, which could be that people spend most of the time either sitting or standing. And we can also see some other inferences, like some site level patterns in the data with some peaks and valleys occurring at regular intervals. And this is change point detection, which seemed to be very effective while doing my analysis. Here we can clearly observe how the activity has been changing at what point. all the x, y, and z values are exactly moving at that similar point, and which we can clearly observe it over here, like at some point that it's changing the direction, and that could really be captured using this method. We have used Rupture's library to perform this. And coming to machine learning models, we have used various models, right, from very simple model to getting closer to a complex model. And here are the accuracies that we have observed during working each model. And it seems that the random forest outperformed when compared to all the other models. Um, So for model development, as you can see that we have experimented with various models. The random forest classifier emerged as the most accurate. Hence, we have also done some multi-class classification using ROC curves to interpret how each label or class is showing performing during the analysis. And since we found that random forest classifier is outperforming, we have also conducted hyperparameter tuning to optimize the random forest model to enhance its performance. And the tuned model achieved an accuracy of 80.98%, it demonstrating its robust classification capabilities. Our results highlight the effectiveness of random forest classifier for human activity recognition. It not only provides accurate predictions, but also insights into classification performance for each activity. So, in conclusion, our project contributes to the realm of human activity recognition. The random forest classifier proves to be a powerful tool for developing personal activity monitors, offering precision, recall, and FN score metrics for comprehensive evaluation. Still, we could find some limitations that I believe which could be worked on during the future exploration of these projects. Like while a model excel, we acknowledge limitations such as the challenge of analyzing activity sequences without temporal information. And future work could include refining temporal feature engineering and exploring additional features and considering real-time implementation, and also could be deployment as well. And thank you so much.